So in the previous video, we looked at some pictures on the GeoGebra worksheet, and I talked about sums and partial sums and convergence sort of in a heuristic way with those pictures. Now I want to make it a little bit clearer what's going on. Specifically, here's the actual definition. So we have a series, an infinite series here, some sequence an, but now we're adding up all the terms, right? So what I want to do then is to give some meaning to what it means to add up that infinite number of terms. In order to do that, we're going to first start with a finite number of things, a finite number of terms, and let the number of terms go to infinity. So very much similar to what we did with improper integrals, where we did an integral over a finite region and then let that region go off to infinity. So it's the same idea here. So I'm going to define the nth partial sum as Sn, and now I apologize, and before I had like a big n and a small n and stuff. This is the way your book has it. It's going to use a sub I for the index for the partial sum. So this is going to be the first n terms of my series. I'm going to add up a1 all the way through an. So that's what we're going to define as n, Sn, the nth partial sum. Okay. And now, in order to determine if I can make sense of this as n goes to infinity, I'm going to look at what happens to this partial sum Sn as n goes to infinity. So we're going to say that if this sequence Sn converges to a finite limit S, then we're going to call the series convergent. And we're going to say that this series converges to S. So S is the sum of the series. So essentially, this is very similar to what we did before, right? Where we took a limit of something. We had something going to infinity. We took a limit of something, and that n goes to infinity. The only difference here is now we're talking about sequences and series. And the other thing that can be confusing is that there's actually two sequences involved, right? We have the original sequence of numbers an that now we're adding up to get the series. But then we also have the sequence of partial sums, which is somehow a sequence that derives from each time you add one more term. All right. Now, in the case that this limit doesn't exist, we just say that the series diverges. So if you want to take a quick look back at the GeoGebra worksheet, just to kind of put this into perspective, we had this problem, right? The 1 over 2 to the k minus 1. And so these are the partial sums, right? And in this worksheet adds up each partial sum. So if I do the second partial, okay, that's S5. I went too fast. So, okay, that's the second partial sum. I'm adding A1 plus A2. And then the third partial sum, fourth, etc. So as I add more terms, as we saw, as you add more terms, if there is a finite limit, you're getting closer to the limit. Okay, so you can see, but what this does here, what it graphs, what it's graphing here, these dots are the partial sums. So this is S1, S2, S3, S4, all the way to this is S12. Whereas these dots are the A's, A1, A2, A3. These are the ones that get added up in order to make these ones down here. So you have in this, which is what's nice about this worksheet, is you have a picture both of the original sequence that you're adding up and then the sequence of partial sums. Okay, so this is one example. This was like the canonical example that we had of something that really looks pretty much like it goes up, it goes to 2. And then I believe, let's go up here and look again, just so you can kind of remind yourself of this particular divergent sequence. We had this. And here, what you see is the A's that we're adding up. They are looking like they're getting close to 1. But then these partial sums, see if I can make it bigger again or smaller or however it is. So these partial sums are just going up higher and higher and higher. And you can see that each time I'm going to be adding another 1. So these partial sums are going up. So if I look at this sequence of partial sums is diverging to infinity, whereas my previous sequence of partial sums was converging to 2. Okay, so that's just sort of those pictures. Feel free to come back to this worksheet and try some of the different pictures. So the question is going to be, how are we going to figure this out? Because from using this definition, what it's going to tell me is in order to make sure that this thing converges, I have to write down what these partial sums are. Okay, so I'm going to tell you right now that that's not necessarily easy. This week we will do some where you can, and then later on we'll also learn some different techniques so that you can tell whether the series converges or diverges even without those partial sums. Shouldn't have done that. What I wanted was to do an example where we show a series diverges when we can actually compute the partial sums. So here's my series, n equals 1 to infinity minus 1 to the n. All right, so what is this? It's minus 1 plus 1 minus 1 plus 1 minus 1 plus 1, etc., right? So that's kind of weird, right? It's either like minus 1 or it's 0. We can show that because the first partial sum is just the first term, which is negative 1. The second partial sum, I add up the first 2 terms of the series, I get 0. Third partial sum, same thing's going to happen. I'm adding up the first 3 terms, minus 1 plus 1 minus 1, I'm going to get minus 1. And I'm going to keep going. But you already see how this is going to go. So if I look at this, what is this sequence Sn? This sequence Sn is going back and forth between minus 1 and 0. So yeah, it's a bounded sequence, but it's not converging, right? It's bouncing back and forth. So the limit n goes to infinity of Sn does not exist. So that tells me what I can say is that this series diverges. Okay. So that's an example, but this example makes sense and it's pretty easy to do because these are very easy to write down, right? Because we can immediately compute a couple terms and see a pattern that happens. So in the case where you can compute some terms and see a pattern that happens, this is a great way of looking at these problems. So we're going to go through a couple more examples where we can do that.